2, 1. All right, welcome to 1C Notes Pre-Calculus.
G'day mates, this right here is linear function y equals x. As you can see, this graph has a domain and range of all real numbers, considering the graph goes both ways with no detriments.
Hola, since it's a linear function, it's not bounded because it goes in both directions.
Cheerio! As you can see, the linear function is an odd function because f of x equals x and the opposite of f of x equals negative x. For example, 1 equals 1 and negative 1 equals negative 1. For discontinuity, there isn't because linear equations are constant. Yeah, there's linear discontinuity because linear equations are constant.
Okay, I'm here to talk about the three parts of this function. First off, we have the increasing and decreasing intervals for this function. Y equals x only increases, so the interval is negative infinity to infinity. Remember, both values are written with parentheses because they are excluded. Next, we have extrema, or the important parts of the graph of the function. We have extrema, the most important parts of the graph of the function. Y equals x does not have extrema. Okay. So last we have end behavior of the function. All end behavior statements should be in limit notation as shown here. So when x approaches negative infinity, y also approaches negative infinity. When x approaches positive infinity, y approaches positive infinity.
As you can see right here, this is a quadratic which is bounded below. This is a continuous function, which means it goes on forever, and this is all real numbers for domain. Although, since bounded below, it'll only stay in quadrant 1 and 2 and start at 0 and end at infinity.
Quadratic functions are even because y equals x squared is equal to the opposite of y equals x squared. They are equal, which makes them even. For discontinuity, quad functions are continuous, which means there are no holes in the graph.
So boundedness. Now we're going to talk about the boundedness and asymptotes of the quadratic function. As you can see, this function has an absolute minimum value. That means that it's bounded below and not above, because it keeps going in both directions. No asymptotes because the line just keeps going.
Hey, I'm back with three parts of a function, but this time for y equals x squared, the parent function for a quadratic function. First, we have the increasing and decreasing intervals. Y equals x squared increases from 0 to infinity and decreases from negative infinity to 0. Don't forget that the 0 is written with brackets to show inclusion. Okay, extrema. Y equals x squared has an absolute minimum of 0 at x equals 0. This is written in a special notation shown here. Finally, we have end behavior. As x approaches negative infinity, y approaches infinity. As x approaches positive infinity, y approaches positive infinity as well.
We are here to discuss cubic function.
The cubic function's standard form is y equals ax cubed plus bx squared plus cx plus d.
Its parent function is y equals x cubed.
It has a domain of negative infinity to infinity.
Its range is all real numbers. It has odd symmetry.
It is not bound, has no discontinuities, and is always increasing.
So today my group and I will be presenting you an example of an inverse linear function. In our pre-calc textbooks, inverse linear functions are often referred as reciprocal functions.
So what is an inverse linear function? An inverse linear function is a function that undoes the action of another function.
Now let's practice analyzing our inverse linear function. So first, to find the domain is negative infinity to 0 union 0 to infinity. To find this, you can use your vertical asymptote or by setting the denominator not equal to 0. Then to find the range, you can use the horizontal asymptotes. And it is 6.46 0 union 0 to negative 6.46. Then to find the end behavior, you also use your asymptotes. In this, as x approaches negative infinity, y is equal to 0, and as x approaches infinity, y is also equal to 0.
So with this function, we don't have any extremas. Extremas are usually absolute maximums or minimums, where in our case, we can see from our graph that we don't have either of them. We do see a decreasing pattern in our function. Our decrease shows at negative infinity to 0 union 0 to infinity.
Now for discontinuities. In our equation, we have a continuity that x cannot equal 0, and for the asymptotes, we have a horizontal asymptote of y equals 0, and our vertical asymptote is x equals 0. Now let's see how this ties back to our domain and range.
Looking at the graph, you can see that the graph is bounded above and below at about x or y equals 6, and if you look down here in the table, it shows that the function has odd symmetry with an origin, and you can tell this by when you put it into the chart. When you put your function into a chart, it gives you the opposite values.
We'll be talking about parent function number 5, which is the square root function. The equation is y square root of x. As you can see on the graph, it has no symmetry and it is bounded below because it doesn't go past the origin.
It also has no vertical asymptotes and no discontinuities. The function has an increase of at 0 to infinity and no extremas.
For end behavior, as x approaches negative infinity, the function does not exist. As x approaches infinity, y approaches infinity.
Lastly, the domain is 0 to infinity, and the range is 0 to infinity.
Exponential functions. Exponential functions can either have growth or decay. The formula for the basic exponential function is b to the power of x. We have two examples of exponential functions. The first one here represents growth, because the b value, that is 2, is greater than 1. The second one represents decay, because the b value, 1 over 2, is less than 1. The symmetry for both is neither even or odd. On the graph, the function is not similar in the opposite quadrants.
For both types of exponential functions, it's bounded below. Both functions do not go in the negatives on the y-axis. There is no vertical asymptote, but the horizontal asymptotes for both types are at y equals 0. However, the parent function will flatten out in quadrant 2, while the parent decay function will flatten out in quadrant 1. There are no discontinuities.
The interval for a parent growth function is increasing for all real numbers. For a decay function, it is the exact opposite, where it's decreasing for all real numbers. There are no extremas because there is no change in the direction of the graph, meaning there's no true or absolute maximum or minimum. The domains for both types are all real numbers. However, the range for both is between 0 and infinity. For parent exponential functions, the y value will never be negative. The end behaviors are flipped. With growth, as x approaches infinity, y does too. And as x approaches negative infinity, y approaches 0. However, with decay, as x approaches infinity, y approaches 0, and as x approaches negative infinity, y approaches infinity.
We have logarithm functions. We did log of x, so that's the base of the equation. The domain is 0 to infinity, since the function never touches 0. The range is negative infinity to infinity, since the function touches all y values. The symmetry is neither, since you cannot have a negative log of the function is not symmetrical. It is not bounded.
Because the range touches all real numbers, the function has no horizontal asymptote. As the graph is shown, it increases from 0 to infinity. There's no extrema since it's continuous and shows no change in direction. As x goes as far as it can to negative infinity, y reaches negative infinity, and as x goes to infinity, y reaches infinity.
Our next parent function is number 8, absolute value function. The equation is y equals the absolute of x. This function has even symmetry when you insert x to the pattern repeats. It is also bounded below. This
function has no asymptotes and no discontinuities. It increases from negative infinity to infinity and decreases from negative infinity to 0. Then there's also an absolute extrema of 0 at x equals 0.
Lastly, the domain is from negative infinity to infinity, and the range is of 0 to infinity. The end behavior is as x approaches negative infinity, and if the x approaches infinity, y approaches infinity for both.
This is the greatest integer function. The parent function is y equals the greatest integer of x. It is also known as the floor function or the step function. The domain of this function is all real numbers, and the range is all real integers. As you can see, the segments on the graph lie where integers would, creating the range.
This function has no symmetry. It is a boundless function because it has no maximum or minimum. There are also no asymptotes. Each integer of the graph has a jump discontinuity between it. This discontinuity is non-removable because this function only includes integers.
This function is constant on each of the separate steps, and it does not possess any extrema. The end behavior of this function is as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity.
In order to graph this function, you round all numbers down to its greatest integer. For example, in order to find the y value for x equals 1.5, you round it down to 1, thus getting the point 1.51. You graph it as the integer which is less than or equal to the value.
This is the logistic function. 1 over 1 plus e to the negative x is the base equation. The domain is negative infinity to infinity. since the function touches all of the x values. The range is 0 to infinity since the function touches all of the values above y equals 0. There's no symmetry because the function is continuous, and it's bounded at all possible x values.
There's no vertical asymptote because it touches all x values, but the function does not touch y equals 0 or y equals 1. There's no discontinuity because it is continuous. It increases from negative infinity to infinity because it touches all possible values of x. And as x approaches negative infinity, y equals 0, and as x approaches infinity, y equals infinity.
When we plug in the function sine of y equals sine of x into the calculator, the graph of this function has a domain of negative infinity to positive infinity, while the range can only go from -1 to +1. And also looking at the graph, we have x-intercepts at -2 pi, -pi, 0, pi, and 2 pi, while our y-intercept is only at 0.
The symmetry of y equals sine of x or anything else is always going to be odd. Our extrema or absolute maximum of 1 at x equals pi over 2 plus 2 pi k, where k is the element of the set of all integers, an absolute minimum of -1 at x equals 3 pi over 2 plus 2 pi k. This means that the function is bounded above and below. The end behavior of this function is oscillating because while continuous, the function values oscillate between -1 and 1 without approaching any other number.
The second function is y equals cosine x. When we compare this to the last function, we see that the graphs have the same shape, just translated over. The domain of this graph is also negative infinity to infinity, and the range is also -1 to 1. The y-intercept of this graph is 1. The symmetry for y equals cosine x will always be even.
The extrema are absolute maximum of 1 at x equals 0 plus 2 pi rk, an absolute minimum of -1 at pi plus 2 pi rk. This function is also, like the last, bounded above and below with oscillating end behaviors. We don't need to know about the specifics of these two functions until later. We just need to be able to differentiate between the two.